Check. Check. On. I just want to check if I'm audible at the back. Okay. If at any point my voice drops, just let me know. Is it all good? Yeah. Yeah, and I can adjust the length based on.
So finally, we are here, the last session of this workshop. And now we have two talks. The first talk will be given by Mansi Sood from MIT on reliable inference at scale using graph structure. Mansi.
First of all, I'm really grateful to thank Siva and Rajat for this opportunity. It's my first time at ICTS. Is it working? Testing now. Should I try holding?
Check.
I'll try to speak up. So thank you for the invitation. It's my first time at ICTS and also part of this program, and I've really got to learn so much. I come from more of an engineering background, but networks has been a theme that's always fascinated me. And I truly think if we look at a system like close enough, there's a genuine networks question that arises from each context. To put some of the directions that I've worked in context, I'll just start by saying what are different contexts in which I have looked at networks, and in particular, what are the nodes and edges. So broadly speaking, there are three broad areas in which I've looked at networks. So first is in the context of distributed systems. You can think of these as a network of mobile devices, a network of sensors, and so on. The other is something that I'm working on more recently. It goes by many names. Sometimes people call them Markov random fields, probabilistic graphical models, directed versions of them are called Bayesian networks. They're essentially, the idea is that the edge, so the nodes are a collection of random variables, and edges or in general other combinatorial objects encode conditional dependencies in your observation. And the third one, which is I think there were so many talks around this theme, is more around the context of social networks, social systems, and contact processes where the edge is a pathway for contagion to travel between people. And you can ask many different questions in all of these contexts. The types of questions that I have looked at in the first thread, it's been actually a network design problem. So here, and this is what I'm going to focus on primarily today. Here, as you will see in this talk, the notion of a random graph or a probabilistic rule to construct a network is actually a design choice that an engineer can make. So there is a very direct connection between some of the distributed algorithms and random graphs. And the other thrust, I'll not speak about too much, just briefly allude to them. The second is around learning from observational data, where you're trying to encode dependencies as graphs. And what this representation helps us is trying to come up with computationally often more efficient ways to learn. And finally, in the context of studying contact processes on networks, when the pandemic was happening, I looked at trying to model if you have a contagion that as it propagates in the network, there is some chance, some structure around if it could mutate, what would be the epidemic characteristics. These are some of the works that I've done on this. And today, I'm going to mostly focus on this first thrust. And just to sort of put my talk title in context, so here structure will come up as various notions of connectivity. And there will be this theme of efficiency in terms of if you're in like a setting like a collection of mobile devices, you want to have utility and be able to do useful things in the network without having to communicate too much. There's also a notion of computation as efficiency, is how much computing you need to expend to learn. And throughout, I'll also allude a little bit to various modes of heterogeneity that come up in these contexts. And I would like to acknowledge all of my collaborators. And for today's talk, most of the work is in collaboration with Osman and Jan. All right, so here is a broad outline of my talk. And in addition to this, given the audience and so one of the things that I've loved about this campus is the density of chalkboards. So towards the end, I will actually try to talk about some questions that will be interesting and that will be on the board. So let me dive into this. So just to put it in perspective, so I will now make this, I've been very vague about saying that there is a random graph question embedded in distributed systems. So I'll make that concrete. And in particular, so there are, I think, many notions of expansion and balancing sparsity if you think of the number edges and connectivity. In these contexts, people sometimes try to find methods in which you can get connectivity, different notions of connectivity without expending too many edges, while allowing for a very simple distributed way to construct the network. And towards this, I will introduce random layout graphs, which has been an object, I think, for more than four decades. It's been in the random graph literature, comes up in various names, including random M-orientable graphs. And it's often hidden in a lot of these systems. And then I'll talk about some of the properties that are known about this, and then some other properties that based on the context we looked at were interesting to study, and then what we studied. And I'll conclude with on the board some further properties that would be good for the settings I'll describe. Okay, so now we are in this regime. I'll use toy illustrations for networks. Nodes are now our devices or reservoirs of data. And the edge will be a notion of a secure communication channel. So let me make this more concrete. If at any point you have any questions, let me know. I'm abstracting out a lot of the details of the system to illustrate the key points. So suppose following is the setting. We are given a graph and we have all nodes on this graph that hold some private values. You can think of these as something simple as like maybe you want to learn everyone's like average opinion, or you could also think of this in the context of those who look at neural networks and training neural networks. These could be gradients that nodes compute locally at their based on the data they have. And then the edge here is the presence of a secure communication channel. I'm abstracting out how that might be constructed, but there's many ways to do that. And then there is no real central authority trying to orchestrate how, for instance, if the goal is to learn just the aggregate sum or average, there's no one orchestrating that process. And this is something that is a problem that's well studied in the privacy and cryptography literature going back to the 80s, where they have a very simple idea. So what they say is each pair of nodes that are neighbors on this graph, what they'll do is they'll compute a mask. One of them will add it to their private value. One of them will subtract it, and they will broadcast this on the network. So for instance, if Rajat and I were neighbors on this graph, we will first of all using some cryptographic keys, or it could be also some other private mechanisms. We will agree to a shared value that you will add to whatever you share with the network, and I will subtract from it. And then the hope is they cancel in aggregate. So just going back, so this was something that was well studied long back. There were several innovations that came up over the last decade when people tried to look at situations where these weights could be really, really high dimensional, such as when you're training neural networks and you have gradients. And then the other thing is there could be lots of nodes and devices that come and go, and they could drop out. So you could imagine if lots of nodes dropped out, their masks wouldn't get cancelled. So there are ways in which people have innovated to make sure that you get utility in that. Okay. But for the purposes of our talk, all we have to remember, we're given a graph. Everyone has a private value. Our goal is to compute the aggregate, and then we do this pairwise masks based on the edges of the graph. Now, in a lot of these contexts, when there's questions of security and privacy, I'd also like to make this connection for those who haven't seen it. I think we looked at percolation in a lot of contexts. Often people talk about like adversaries or like nodes that you do not trust as occupying some sites in the network. So these could be a random fraction. These could also be an adversary who has maybe the global picture and tries to go for the weakest links, weakest nodes that will be most useful fit. So now suppose in this toy model, at sites 1 and 6, we had nodes that are sort of trying to de-anonymize or recover individual weights of these other nodes. And they can also potentially talk to each other. So in this, what happens actually, all of the masks that are generated with adversarial nodes are effectively useless. And in particular, I don't have a very clear picture, but what actually happens is you think of the mask, you can think of remove all of the nodes that are adversarial, look at the subgraph that remains, and that is only what is going to be having the masking. So in this process, what one would want is to design this network well enough so that even if there's some adversaries, After you remove the network, there's really no node that's like isolated, like this little node on the right. It'll make all of this a little bit more concrete. But I wanted to share this application because here there is this sparsity connectivity trade-off manifesting. So if you had all the resources in the world, you just organize these nodes in a complete graph, generate as many masks as you could. But in practice, that would entail a lot more communication, like in terms of generating these masks, and imagine running this for many, many steps in something like a gradient descent algorithm for really high dimensional vectors. So one of the innovations that has come up in this area is to go from complete graphs to graphs, like regular graphs, something that could like have good connectivity, but without requiring too many edges. So there is this inherent trade-off. The catch here is we want to get a good trade-off on this while also having a way to construct the network that's easy, lightweight, can be done in a distributed way. There's no notion of which node connects to whom, and so on. So this object actually, I'll say like how recent like works in this more applied context. Use a model like this without actually, I think, realizing it's a graph that's pretty well studied. I don't know if there's an earlier reference of it, but I saw it as appearing in the 80s as the random M orientable graph. So now let me describe, and now I think the authors call it, from that paper, call it random chaos graphs. So let me describe what this is. And yeah.
What are these masks like typically in practice? Like what kind of mask somebody provides?
So I think there's usually like a key exchange protocol, like a Diffie-Hellman key exchange protocol, where you and I share like a cryptographic primitive. And based on that is not usually that big. And then you use that to generate a mask. And I've seen them appear in both contexts. One is like statistical noise that people add. The other is also like more cryptographic. Happy to like direct you to more. I will also cite some of those papers now. So now just talking about this object, I think it comes up in, I'll not be surprised if a lot of you would have seen it with another name in a more general context. But for those who haven't seen it, so this is one way of constructing a random graph. Given n, which is the number of nodes, we have just one parameter, this capital K, with aiming to make an undirected random graph. There are also variants which get to a directed random graph. But here, say, just as a toy illustration, suppose we want to generate random 2-out graph on 6 nodes. What we'll do is each node is going to select k other neighboring nodes uniformly at random from the remaining graph. Each node is going to do this, and we say there will be an edge between 2 nodes if either of them has selected the other. So this is one of the random k-out graph. One thing that is nice about this is one was, of course, there was this whole distributed construction, and it has pretty good connectivity properties. So it was well known that as long as this k parameter is 2 or more, you're going to get a graph that's connected with high probability. And then what this means for practitioners is, so in this graph, you can see the average node dB would scale roughly as 2 times this parameter. So if you were just trying to go for connectivity, just an average degree of 4 would be enough. And it's, of course, you could have done something better, like trying to just go with random regular graphs, but say compared to often when people use Ardashrini, this is pretty good because you don't have the average degree scaling with a network size. So one of the first things we did when we started looking at this object, so our motivation throughout was trying to see in a lot of practical context, people were trying to decide how to choose these parameters to get, say, this stamp of connectivity, and that would translate to certain privacy guarantees. So we derived, we used the framework in our paper and then extended it with some other bounds to derive finite n upper and lower bounds on this connectivity. And then asymptotically, we showed that this is order-wise optimal. Okay, so far so good. I will go back to the application in a bit, but just bear with me. So the random chaos graph was a pretty good object to consider when you wanted connectivity in a distributed context without expending too many edges. Moreover, I've not talked about it, but it also has certain other connectivity properties that will answer some of the questions that we began with. And then and again, there were people started, I think, in the random graphs literature also. I think sometimes these objects appear, I've seen it appear as random diagraph, but I think it can mean a lot of different things in different contexts. But one simple question to ask is, what if there is a small fraction of nodes which did not make these two selections? And would you still have as good as connectivity and like other properties? So this is the other object I'll talk about. And in an applied context, if some of these edges or masks fail, you want to be able to study what will be the result on the connectivity and other notions of it and so on. So this is just the simplest extension. Consider that each node is endowed with a type. With a coin toss, you assign it to be a type 1 or type 2. We assume this is a constant that's strictly positive, doesn't scale with n. And then based on this, you have a similar procedure. So suppose here the blue nodes were called type 1, they just select one other node. The red nodes are called type 2 and they select, in this picture, 3 nodes. Similar way, you construct a graph. There is an edge between 2 nodes if either of them is selected. So now I'm going to switch. So I've introduced the broad motivation. I've introduced the specific random graph model. Now I will make a little bit of a more concrete connection between, in those contexts, some properties that would matter. Yeah. Okay.
I also want to add a question on the model. So the edge exists if node I selects node J, and that's regardless of the type, right?
Yeah.
In type independent edges.
Yes, yes. Okay. Thanks for that question. Yeah. Okay. So now I'm switching back to the more applied context. I do want to, so there's actually so at the time when I was doing my PhD, I was also affiliated with the Privacy and Security Institute. And this model, whatever you would like to call it, was appearing in sort of disguise in a lot of these settings. And often what practitioners would do is try to take an Order-Shreni graph with the same average degree and try to say how should we set the parameters. So there are all of these applications, I can talk about them. But this is one application that this one I talked about a little bit briefly. Okay. So let me first fully tie this. So some of the questions that are interesting now. So I already showed you there could be, in this setting, their edges are masks, and then there could be some sites that are occupied by adversaries. You would want to ensure at the time of designing this network, if you know a priori how many adversaries you might have, how could you ensure that even when they are present, that your network is connected? So, and I like to think about this in 2 contexts. So one is like a very powerful adversary, which can like occupy the sites, whatever sites would give it the most information. The other is maybe more like the percolation case, where you could have like either a random subset of nodes or with an independent probability, you can have an adversary occupying the nodes. And then I thought, like, at least for the targeted subset of nodes, what one could use is the property of k-vertex connectivity. And I will make that concrete in a bit. But just when we are at this layer of applications, I want to make this interesting connection. I think it was something I realized while working on this model and talking to all of these different contexts. This is actually something called secure aggregation. This is paper from authors, I think, at Google Research. So I was now talking about starting with this communication graph. So in their context, it's often what is known as federated learning. So the graph is a little bit more abstract. So you have a server that can facilitate your communication, but these edges actually, there are ways to generate mask. So it's like a virtual graph, but the idea is similar. And in these contexts, if you see like the exact same graph is constructed as follows, each client is making so many selections from other nodes. You have an edge if either they choose them or you choose them. And I'll talk, and somehow perform, like there wasn't a good characterization of how, if you were giving a certificate of privacy guarantees, how would you handle different adversarial models. So that was a nice connection, I think, that I realized. I'm also aware that I've spent a lot of time on the context. But now let me just dive in. I think for this, the audience in this room, this is maybe like a very familiar slide. But one way of thinking about connectivity, especially from a more practical lens, is going from like something like a weaker to a stronger notion of connectivity. So one connectivity we already spoke about, and if I let C max denote my largest subgraph, so it's essentially saying that's all of your network. So one object I've looked at a lot is K connectivity. There's different, so there's K vertex connectivity, K edge connectivity, and so on. But we'll mostly talk about K vertex connectivity, and what it does is it ensures that your network stays connected despite any K-1 node failures. They could be anywhere in the network. So it's sort of like then a worst case attack mode. And then, but sometimes in practice, you may not really be able to generate a network that has so many edges or has so many masks. So it's often also useful to characterize the largest component size. And in particular, actually, ideally, if we could characterize the distribution over all components, that will be even better. I'll talk about that in the end on the chalkboard, but these are some ways of thinking about it. So, okay. So in these contexts, one way to think about what properties might matter, this is by no means like an exhaustive characterization, is to say, okay, so we had the most vanilla, I'm calling it homogeneous random K-out graph. And suppose, like, let us not make this K something like that's finite. Let us in general allow it to scale with the number of nodes in the network. Then we introduced this object, which was very one simple way to introduce some inhomogeneity, where you have each node be assigned to a type. And then based on the type, it determines how many selections it makes. We considered the simplest case where there is, with a strictly positive probability mu, a node that makes just nodes that make just one selection, and the remaining can make number of selections Kn that scale with the number of nodes in the network. I apologize with the overloaded K. So there's little k for the K connectivity, capital K for the K out graphs, but since these were the definitions for these objects, I stuck to them. Okay. So I already talked about this result, which said that for the homogeneous random K out graph, these two actually didn't have to scale with n, 2 was enough. And then moreover, there were results in the same paper which said that if you wanted K connectivity, which was, say, if you had 5 connectivity, means your network is going to be fine in terms of connectivity. You can take off any 4 vertices you want, but it's going to be fine as long as you set this parameter to 2 times this little K value. So there was work showing that the moment you introduce some inhomogeneity in this model, so if you have, there is for each node a strictly positive probability of it picking less than 2 nodes, then you have the remaining nodes, if there were just 2 types, they have to have a Kn that grows unboundedly with the number of nodes. And then some of the questions which we looked at were, one, so this is something I already showed, like whenever possible, can we give something that holds for a finite number of nodes? Then what if there are different modes of attacks, either captured through K connectivity or like a random subset of nodes? And this is I want to also make a note that this is an object, even referring back to Ganesh's open problem talk. So he talked about, I think he mentioned D out graphs. That was a bipartite version of the random K out graph. And there are many other variants that are studied. Some of these I'll talk about towards in the last maybe 10 minutes on the chalkboard. Okay. So what are some of the results? I think, so what we tried to do was, one, so for this property in particular, we derived a 0-1 law. I'll talk about how we came to it. For the homogeneous K-out graph itself, what we tried to look at is if you have different subset of nodes that fail, when the subset of nodes that fail, what can you say? I think this would be square root of n. But how should you scale K so that you are guaranteed to have either one connectivity or a largest connected component greater than a certain threshold? And we've done this for different regimes. I am happy to direct you to references on this. And then I will just spend a minute talking about, I also want to talk about this because I think when I was like looking at this object, I really used like the very basic method of moments type of approach. Like I'm curious if, as you see, like the arguments, if you think this object could, and this property could be handled with some other, I think, clever way. So this is sort of the result we had for K vertex connectivity on this extended sort of random K out graph, where there is a parameter in addition to Kn, there's a parameter mu. A node with probability mu just makes one selection, and then with otherwise it makes Kn selections. So this is sort of the threshold we got. We didn't characterize what's happening between 0 and 1. And this is just like an empirical sort of illustration with finite nodes. So I'd given this talk to an engineering audience, so this might be redundant for a lot of you in the room. So essentially used method of moments. I think it's like one of the most basic things one can do when dealing with combinatorial objects. So I will not go over this, but I will just say that the most challenging part for this model tended to be dealing with this one law, in particular with sending all of these limits appropriately. And as you can see in this graph generation mechanism, there's correlations between presence of edges between nodes. And even more with this mode of inhomogeneity that we introduced, if you make an edge, you expanded an edge, but it could also potentially make you more likely to be of the type that makes more edges. So yeah, so just going to very quickly show like how we thought about it. I would be very keen to see if like some of the tools and concepts we've learned, I think, over the week. Yeah.
So for this random K-out graphs, so in the previous works, was K ever random or?
So in a lot of the work by Alan Fries, K is often fixed.
Okay.
So one of the other papers I had, in that what they looked at was, it was a directed, more general version of it, where K could be sampled from a distribution. And I think they were trying to see for the directed version of that, what happens to the component size.
So your K can also be thought of as a random K, right? So if you look at the annealed law, but are you fixing the type 1 and type 2s first and then doing this, or?
Yes.
Okay.
So I think for me, one also like curious question is, so my guess is if the property we were going for was the largest connected component, there would be a lot of results already. Like I'm not sure how, if we are looking for something like, for instance, K vertex connectivity, how some of those would apply. And I will try to save some time and I can go to some of the questions I have in mind for, I think, especially being in this audience. Okay, so this is just saying that even if you had a connected network, the minimum node degree and K vertex connectivity are not the same properties. Minimum node degree often is easier to reason about, but then doesn't guarantee K vertex connectivity for free. In particular, in this graph, you are connected, all nodes have a minimum node degree of 4, but you do not have K vertex connectivity. So how we reasoned about this, we just first argued about the minimum node degree and got it phase transition. To the room, I'm also curious if there are like more general results which say that if you've established a law for minimum node degree, can you always guarantee that there will be K connectivity following the same threshold? So that is that for K is okay, but in general for a larger K, like I am not sure, and especially for a model like this, but like that would be very, very cool because we got the same threshold for K vertex connectivity. And how we did was essentially, so the minimum node degrees, one of the laws automatically, so if you do not have a minimum node degree, at least little K, you're not getting K vertex connectivity. But for the other direction, I think we did again something like super first principles. We tried to see, so if we already established the result, so delta is your minimum node degree for it, but then could you say, like use this to show a result on the k-vertex connectivity? And then what we tried to see is look at this event of having a k-vertex connectivity at least k as this difference between the minimum node degree being k and then the minimum node degree being k, but the vertex connectivity being less than k, and sort of defining simpler and simpler events. And then there was ultimately we landed at this situation where there is a vertex cut that fragments the graph and it's of size L. And like in the interest of time, I will not talk about it, but this is how we reasoned about using a result for minimum node degree that we derived to take it to k-vertex connectivity. Okay, so I will summarize this, but I really want to take some time to think, to sort of have some problems that are really important in practical context. But just to summarize this, so what I talked about and hopefully motivated enough is distributed network design. Balancing sparsity with connectivity is pretty important. So there are obvious implications like being able to communicate and some indirect implications like privacy mechanisms. So random k-out graphs was an object that in these applied contexts was appearing over and over again without necessarily being attributed as being that model. Often practitioners were using Gaussian graphs to approximate them. Yeah, so this is something, and it's really I did not talk about it, but even like in cryptocurrency networks, people like anonymity preserving routing use something like that. So it's systems that are decentralized with limited trust, often this comes up a lot. So we tried to characterize properties in different operational contexts, albeit it wasn't explicit. This final bit I would like to do on the chalkboard. I'm almost out of time. Okay, this I will not speak about, but what I realized, I was thinking about these objects for so long when I started reasoning about these probabilistic graphical models. The way they define independence is actually a lot like connectivity. So I'm happy to chat more about this. So this is more about distribution learning, and here also combinatorial structure comes in. But I will skip this. And I really like this as a motivation for me. I think our world is so complex. I always feel like a network perspective brings in a lot of insight. I'm planning to be here between 4 to 7. My jet lag is finally gone to chat more. I do want to spend some few very rapid minutes on the chalkboard to talk about, I think, some properties that would be interesting to consider. So I have about 5 minutes, right?
Yeah.
Okay. Okay, awesome. If I wanted to send this up.
Yeah.
Okay, awesome. So sorry for the abrupt transition, but I was really excited because these are some properties I've been thinking about, and I feel this community might have answers. So just first was this whole context that I was talking about. You have a graph, say it's made with the construction similar to what I defined. You have certain number of sites that are effectively removed, and then the edges corresponding to them don't matter. So then it would be really nice if we could have for this. So this is just, I'm calling this. So what ends up happening in the graph that remains, you actually in those algorithms get partial sums. So if your h and k was the object you began with, and there was, say, a fixed number of deletions, or you could even think of this as a fixed fraction, could you characterize distribution of component sizes or some approximation of? Because these sizes actually have, like, connections with partial sums that are revealed, and I think it would be really cool. One more thing, I think that so far, I think isn't some.
Mansi, these deletions are known, like how many you delete? You have this number, like...
I think the way you'll think of this is, if I'm designing this method, I will take a budget of what is the adversary's power. And that will be an assumption you will work with to begin with. You could be conservative to begin with, but that's how usually. And often it's very much related to like fraction that, so like I think percolation and all those things would be useful there. The second thing is, I think it touches upon some other, like I think for instance, some of the objects we've looked at. So I did not talk about, I think, physical proximity or geometry at all. So I think, so there's already some work, I think, by Alan Fries, which talks about random layout subgraphs of large graphs. So here, essentially, instead of making your selections uniformly at random from all the other remaining nodes, you begin with a graph that constrains how you can make selections. I don't think all of the properties are well understood here. The other thing is, this is maybe like I think Nelly gave a talk on random geometric graphs. One thing I feel, I don't know how much it is studied, but if one could sort of take the random layout graph and then remove all the edges that were not between nodes that are proximate enough, like say for instance, by using the random geometric graph, what can you say? I think that will be another thing that would be interesting. Also, nodes that come in later. So if you already had a graph and there were nodes coming in later, how could you think about what mechanisms you could use? One thing I think, since that was also like proximate to a talk we had in the morning, I don't know how to deal with this, but if one could give the spectral properties in particular, or any approximation of it, of the second smallest eigenvalue of the normalized Laplacian, I think that will be very nice because it often relates to convergence of many, many runs of algorithms that are happening on this. I'll now make it really quick. So there wasn't an exhaustive characterization we did. So there's homogeneous, there could be inhomogeneous with like Rajat mentioned, like, or Shayan mentioned, like a distribution. And then you want to characterize all notions of connectivity to the best possible way, while saying if you could have like finite n bounds whenever possible, and deal with deletions.
A little bigger, we can't see from so far. A little bigger. Font size, yeah.
Let me read it out. So in this context, with that. And I think finally, I'd like to say that, okay, so this is fine. And I think in the interest of time, I will conclude here. I'd also just like to say that I feel often in a lot of contexts in AI, where there's AI infrastructure, the network structure is really important. But often what I see practitioners, this will complete this sentence, test their algorithms on is either something like Doshlini or cycle graphs. I feel if we could visualize and like communicate like all of the different models there are, especially like I think both of these models I feel as well, and what all properties we can characterize. I think that will be really cool. But I think, thank you. I am out of time, but thank you so much.
Questions, comments? Kumarji. Yes.
So any study on cover time on random K, I mean, conditional that it is connected.
Sorry.
Conditional that it is connected. I mean, it was random K out graph, conditional that it is connected. Any study on cover time on it?
Any study on?
Cover time.
I am not sure. I am not sure. That will be interesting.
For random regular graphs, there are some results on K connectivity. I think the degree and K need to be the same,
Possibly.
or maybe plus or minus 1.
Sounds good.
forget.
Like one thing I'm curious about, it feels like this object is trying to get a random regular, but it's not quite there. Like how far these results are from, because it becomes, I think, complicated to analyze when there's so much rich literature for this. So I don't know if one could use.
That's a problem. Yeah, I know that there are lots of papers also trying to characterize different properties of random graphs in terms of the minimal degree. So the minimum degree 2 is, I think, Hamiltonicity or something like that. So there are some works. I'm not sure whether this also applies to connectivity, for example.
Thanks.
There is also work on using where geometry is involved, in the sense that if you connect to K nearest neighbors, then when K is like log n, then it's strongly connected in the directed setting.
I think it's the K out nearest neighbor. Is that the one?
Right.
Okay.
Any further questions? There is one extremely behind. I have to run too far. Siva.
So I think about the last bit that you mentioned at the very end for the random regular graphs, and especially about the AI server infrastructure. I think there is work in terms of random regular graphs being used for something like that, or certain optimality properties by Tsitsiklis, and very recently, maybe that's something that might be interesting to look at. And yeah, that's just something I want to point out.
So yeah, that sounds very interesting. I'd love to learn.
Any further comments? Okay, if not, let's thank Mansi. Before we start the second talk, I'll take 1 minute to just, it will be a board talk, so erase the board and then we start this next talk. Yeah. We'll have Remco van der Hofstad from TU Eindhoven. I don't know what he will be speaking about, so the exact title is mysterious. So Remco, yours.
Thank you very much.
I will say something more about the organizers later on, because I'm the last speaker. There is not much mystery. I will be talking about the number.
Remco, could you write below the shadow?
You. So if you can't read what I write, and Mr. Chairman, I will also set up the timer. Otherwise, you might not reach your flight. Or maybe you'll do that. Okay, so I have to write below the shadow, otherwise apparently you can't see, so I'll try that. The number and structure of graphs with prescribed or given degrees. And this is joint work with two very bright young women, Sasha Bell. He's a master student of Luigi Adario Berri, and next she has just handed in her master thesis. This is not part of it, so I find that very impressive. And she will start next month as a PhD student of Luigi. She's at McGill. And Seth Donderwinkel. And she is in Groningen. And for those of you who do not know where Groningen is, that's just the Netherlands. That's tiny anyway. So we've seen a very nice talk, beautiful talk, by Anita Liebenau, talking about the number of graphs, various properties, but including specifically focusing on the degrees. So the additional thing that I'm adding here is that we're talking about connecting. Oh, this is not visible. Need to go there. And in some regimes, almost all of these graphs are connected, and we'll be specifically focusing on the regime where they're not usually connected. And then we'll see that there is an exponential penalty for being connected, and we'll give a precise characterization of that exponential penalty, and also an interpretation of where it comes from. That's the plan. And we'll do this in the sparse setting. All right. So let's start writing down some assumptions. So I've been doing this before in my open problem session. So I'll have vertices in 1 to n, which I usually denote by n with square brackets, and a vertex I has degree bi, and I will phrase things in terms of the random variable dn, which is the degree of a uniform vertex chosen uniformly at random. That's a random variable. And I will be assuming that the probability that dn is equal to k will converge to some limiting probability. And that's the same thing as saying that if I look at the number of vertices of degree k, and I divide through by n, that this will converge to pk, which is just the probability that this is equal to k. Okay, so these will come about as well. That's my first assumption. Then I have a second assumption, which assumes that the moment converges to the moment of the limit. So this is a uniform integrability condition. And in some cases, I will also need to assume that the second moment converges. But this is not always the case. clear about when I will be needing to assume that. And then I'll make two assumptions on the limiting degree distribution. So these are about convergence. I'll assume that the expected value of D is strictly larger than 2. And in terms of connectivity, that makes perfect sense, because if the expectation would be 2, we're basically talking about trees. Trees are very poorly connected. That's a regime that is even harder than the regime that I'm going to be talking about. So this is basically telling us that the graphs will not be trees. And the last condition is that P1, which is the probability that D is equal to 1, is strictly positive. That turns out to be a very relevant condition, because if this is not satisfied, then even the graphs are going to be quite likely to be connected. So that's an easier regime, and we'll say something about that later. Okay, so that's the setting that we'll be in. It's a sparse setting. We have a nice degree distribution that converges. So now what are we going to be studying? Well, I will be denoting two things. I will be interested in this degree distribution. This is just a number of graphs with degrees D, and this is a vector. There is 1 up to n. And I will also be interested in the size of the subset. That's my main object of study. That's the number of connected graphs with the same.
Remco, one question.
Yes.
Do you allow simple graphs, or it could be multiple graphs?
Yeah. The non-simple graphs will appear as well, but we'll be focusing on the non-simple graph. Yes, they're labeled. Yeah, because the vertices have labels, right? 1 up to n. Okay, so let me write down my two main theorems. Oh, lower. For this, I will have to introduce some things that will actually describe this exponential penalty for being connected. And this is in terms of a parameter beta, which is the unique, you have to prove that, but it's the unique solution to the equation, the sum over k times pk, is nothing but the expectation of D, is equal to 1 minus beta squared. The sum from k is 1 to infinity, k pk, divided by 1 minus beta to the power k. A bit of a weird equation. We'll later see where this equation comes from, and also what the interpretation of beta is. And then we define the functional k, which is a function of p. Of course, this beta is also a function of p, which is 1/2 the sum over k pk times the log of 1 minus beta squared, one of its contributions, minus the sum over k pk log 1 minus beta k. Okay, that's a functional. And then the result says that the number of connected graphs is equal to e to the power minus n kp plus small o of n times the number of simple graphs. And this we know is the same as e to the power minus n kp plus small n. Ln minus 1 double factorial divided by the product over all i's DI factorial, this was already in Anita's talk, where ln is the sum of the degrees, which I assume to be even, because otherwise there aren't any graphs that are connected nor simple. Okay, so this gives the exponential penalty. This number will be strictly positive. And it's quite funny because this fixed point equation and this functional K already appeared in a paper by Shankar Bhamidi.
Remco,
Yeah.
in the first expression for K of P, on the first line, is it beta squared or beta power K?
This one is beta squared.
So it just comes out as a constant. It's a constant.
Yeah, you
Okay.
could put it in the form.
Okay.
Where they were doing exploration processes and large deviations for that, they were looking at sort of component sizes. They didn't quite treat the connectivity regime, which I'm addressing here. And it's quite funny that it came out there. They didn't quite have an interpretation for it. And actually our work provides it, an interpretation, because beta will be the extinction probability of a certain branching process that is related to P, but isn't quite P. And that is part of my second main theorem. And this theorem we completed the proof while being here. So we now roughly know how many there are. And then the next question is, what is their structure? Okay, we've already seen talks about local limits. So let Gn be in this set that we're interested in, chosen uniformly at random. Random graph from this set. We know roughly how many there are. And now the question is, what is the structure? Here I have to make a stronger assumption, namely that the maximum degree, which is just the maximum overall vertices of I, is less than or equal to K. There's only a finite number of values of the degree that occurs in my degree sequence. Then Gn converges locally in probability to a certain branching process. Branching process, BP, with root offspring distribution. Some Q, and I will write down what Q is, conditioned on survival. And the conditioning on survival is very crucial because the graph is connected. And that means that if you're looking locally around the point, you will have to see that actually the graph extends infinitely far. And for a general branching process, that may need to be the case if the probability of having one offspring is strictly positive. And that will be the case here. So the mystery here is what Q is. And Q, of course, is determined in terms of beta. And it takes the following shape. Exactly the thing that we see coming around here as well. Here you have an extra K. Here you don't. And you have this weighing with 1 minus beta to the power. Okay? And then, of course, you have to normalize. But in particular, Q1 will be strictly positive because P1 is strictly positive. Okay, so this branching process could die out, but we're conditioning it not to die out. Are the two main theorems clear? Yes. Yes, I will. I will say how it comes about. At least I hope. That will be a little bit dependent on time. All right. So here I sort of snuck in an analysis of how large this graph is. And of course, Anita said something about this. But in order to somehow see the structure of the proof, it will be useful to actually go back to that particular problem. So how do we generally do this? Well, we go to the configuration model. And I think at this point in the conference, I no longer have to explain what the configuration model is, so I won't. But of course, we know what the degrees are, we know the conditions, etc., etc. What I would like to write down is the exact graph probabilities, because that's quite useful, for the configuration model. Bear in mind, the configuration model may give a non-simple graph, a multi-graph, where you have self-loops and you have multi-edges. Okay? So suppose that I have a graph G, which I indicate sort of with something which looks like an adjacency matrix, right? So for a simple graph, this would consist of zeros and ones. But in this case, it's a multi-graph, so it can also have larger numbers, and it could also have non-zeros on the diagonal. So this is a multi-graph. And now I would like that this multi-graph actually has the correct degrees. Okay? So I'm going to be imposing that the degree of vertex I is the number of self-loops plus the sum over j in n of the number of multi-edges. But bear in mind, I'm counting there the number of self-loops once more, because of course the self-loop eats up 2 half-edge degrees into the vertex. And I want this for every I. And then the probability that the configuration model of size n and with these degrees takes on this value g and be computed explicitly. And that's 1 over ln minus 1 double factorial. This is even, this is an odd value. Double factorial means that you go down by 2. Okay? Right? And on the top here, we see the product over I, dr factorial. And then there is a correction, which is the product over I, 2 to the power xii, the self-loops. And then a product over I less than or equal to j less than or equal to n, greater than or equal to 1, xij factorial. And this is a bit of counting that you have to do. You count the number of configurations, which are the pairings of the half edges. This is the probability of every configuration. Configurations are uniform, and you count how many will actually correspond to G. Now note that xii is equal to 0 for every I, and xij is in between 0 and 1 for every I and j, then this factor is not there. So the probability that CMN is equal to G does not depend G, on the specifics of G. And that's, of course, exactly the same thing as saying that it's simple. So I can sum out overall simple graphs, and what you get is that the probability of CMND being simple is nothing but, well, how many graphs are there times okay. And out of that, you immediately get, and this certainly Anita had on our slides as well. Okay. So that actually allows you to compute the total number of uniform graphs from the configuration model if you can handle this probability. And as it turns out, under these 3 conditions, and there it's useful to have this 3rd condition, you can actually explicitly compute what the asymptotic probability is of being simple. And the reason for that is that the total number of self-loops and the total number of multi-edges, or the total number of pairs of vertices that have more than one edge between them, that doesn't really matter very much. These jointly converge to 2 independent Poisson random variables with an appropriate mean, and therefore this will converge to the probability that they're both 0, so it's going to be e to the power minus 2 numbers. Okay. That's the way how this goes. All right. So that's all very nice. This is sometimes called the probabilistic method. I'm a big fan of Joel Spencer, and he calls this Erdős magic, which I think is actually a very nice phrase. And the proof of the main result will follow a similar line of argument. So let's highlight here what is the trick. I mean, how can we view this? Well, you could say that the trick is to find an appropriate larger set of graphs, which you can analyze more easily, in which the graphs that you're interested in are somehow hidden. And then if you understand somehow what subset this is, you can also understand this subset. That's sort of what this does. And here the larger graph is multigraphs or configurations, depending on your perspective. And because you can handle sort of the relation between sort of the simple graphs and the multigraphs, actually you get your hands upon the uniform graphs as well, their number and therefore also their distribution. And I would like to do something similar. Yeah.
About the main theorem, if I also look at this as measures, say if you take the uniform measure on the connected components and the uniform measure, so there is sort of an exponential tilting here. It seems like, can this Kp be also be interpreted as some entropy of something?
That's not how it comes out for us, but hang on to that question, because let me try to explain a little bit how the proof is organized.
Another question on the theorem. The pKs notationally are just given by that equation, or they?
I'm sorry? Oh, yes, I should have written in all my further notation, pk is just the probability that these. Was that the question? Yeah? Good. Thank you. Writing pk is a bit shorter than these all the time. All right. Ready for the proof? Okay. So what we'll try to do is somehow find the connected graph inside some other graph. Well, what would be the natural thing to do? Take a bigger configuration model. Okay? So for the rest of my argument, it will actually be convenient to consider type sequences. So this is a slightly different way of ordering the vertices. So rather than saying vertex I has degree di, I'm going to be thinking about how many vertices of degree k I have for every k. Right? So I'm going to write down n of k. I already had this somewhere. This is just the number of vertices for which the degree of I is k. And rather than dealing with this object, which I would normally do, I'm now going to be instead dealing with this object, where this is a boldface letter and that is a boldface letter as well, because these are basically one and one. Okay? So from now on, I'm going to be looking at the total number of graphs or connected graphs, same thing for the connected ones, with a given type sequence. Okay, right. Now, why is this convenient? Well, so I now have my type sequence little n, containing all these elements n1, n2, n3, etc. And now I'm going to be looking at a larger one, capital N, which is greater than or equal to little n, meaning that the number of vertices of degree k here is always larger than the number of vertices of degree k there for every k. And I'm going to choose this n cleverly, namely such that the giant in Cm, let me now just write n for the type sequence, it approximately has type sequence. Little n. Okay. So a giant is a connected graph. And now I have a connected graph that has the right type sequence. That sounds like we're on our way. Now also we know that these giants are very well concentrated. Okay, so if I look at this giant here, it will be very close to, you know, whatever the typical type sequence should be. Okay, so because of that, and simply by counting, we should therefore get that if I look at the total number of simple graphs with this type sequence, which I understand really well, that should be very closely related to the number of connected graphs, because that's the giant, with the smaller type sequence, times the number of remaining graphs. So these will have type sequence n, capital N minus little n. Plus a counting factor, because, you know, all the vertices that I put in here, you know, I can, every vertex of degree I can choose where I want to put it. Okay, so I have to multiply this by the binomial coefficient, which basically tells me in how many ways I can pick these vertices from these. And this looks like a simple binomial, but it's actually a product of binomials. I don't have bold-faced chalk, unfortunately. But this is just a product of normal binomial coefficient. So this basically counts the number of ways how you can choose the different subcollections. Okay? Well, if this is the case, I'm not allowed to go further than this. No, not further than this. Excellent. If this is the case, then I can actually write my quantity of interest, which is this. I've divided both sides by Gn. Well, just do the arithmetic. I'm going to be getting G capital N divided by G little n times G n minus n times this product of coefficients. And if this were to be the case, of course, this is not going to be an equality. Almost equality. If this is the case, I'm done. Okay. Excellent. So that's the proof strategy. Of course, this does not explain yet how we have to choose our larger type sequence, capital N. And that's the next item on the agenda. Any questions so far? Of course, this is only the proof idea. In order to make it work, you have to work with epsilon and delta and so on, but okay. I'm trying to explain the key message here. So the next question is how to choose this larger type sequence. And that's where both the beta as well as the Q's will start playing a role. Okay? Okay, so how are we going to set this up? I'm going to be taking n to be some gamma times n, where gamma, of course, is origin 1. We would expect capital N to live on the same scale as the little n. And I'm going to be assuming that there's a certain type sequence, or a certain limiting degree distribution in my larger graph, where this will converge to this qk. And now what I have to do is figure out what the gamma is, what the qk is. Well, we know what the structure of the what the structure of the giant component is. So if I let Vk C max, you know, the total number of vertices of degree k in my giant, if I divide that through by n, this will converge to something involving this. And it will be qk times 1 minus beta to the power k, where beta is a certain extinction probability of half edges in the configuration model. Okay, so how can we understand this? If I have a vertex of degree k, it has k half edges coming out of it. If one of these half edges survives, then we're in the giant. So the only way how we cannot be in the giant is when they all die out. That's going to occur with probability beta to the power k, and therefore with probability 1 minus beta to the power k, I'm going to be in the giant. That's exactly what this says. Vk is the number of vertices of degree k in this set. Important notion. And I will also look at the total number of edges in CMAP. And I will also divide that through by n. And that converges in probability to, well, 1/2 the sum over k times qk. That's the limiting total number of edges, times 1 minus beta squared. And again, that has a very clear interpretation. If I take an edge uniformly at random, it has 2 half edges. If one of these half edges happens to survive, then the edge is connected to the giant and therefore will be in the giant. And if both sides die out, it's not going to be in the giant. So that's it for O'Neill. Now we already see a little bit of an inkling as to where the beta squareds and the 1 minus beta to the power k come from. But they're in the wrong position, and that's because we're dealing with Q and not with K.
Remco, I have the same doubt as science. Vk is the number of vertices in
Vk of any set. S is the number of degree.
Vk vertices.
Remco?
Yeah.
So b squared, beta squared, you just now explained, but in that main theorem 1, still it's beta to the
Oh,
power
no.
k.
What?
1 minus beta to the power k and not 2k.
Yeah, it's 1 minus beta to the power k.
Okay. So we will hear further why.
Oh, I didn't explain that yet. I didn't explain yet where the equation comes from.
Yeah, but you can.
In fact, that was exactly what was on the menu now.
Okay, good.
Yeah, so there I'm dividing through by capital N, which is the size of my configuration model. But of course, in the end, I'm interested in little n. Okay? So rather than looking at it like this, I'm going to be instead thinking about this. Of course, I know that capital N is gamma times little n. So if I were to divide by capital N, I get this limit. So if instead I divide by little n, I get an extra factor gamma. And the same thing with the edges. Okay, we're almost there. Because I want my giant to be my wanted connected graph with type sequence little n. So this better be pk. And then indeed, the leading order behavior of the number of degree k vertices in this giant is n times pk, which is basically nk. I want this to be pk. Also, the total number of edges in my maximum component here, if that maximum component is going to be my wanted connected graph, that better be the total number of edges in my connected graph, which scales like 1/2 the sum of the k. K times pk. That gives me 2 equations. And a number of unknowns, including gamma, and the Q. Okay? All right. So I'm going to be taking pk to be, qk. I want to know what qk is. To be pk divided by gamma 1 minus beta to the power k. So now we see the 1 minus is also, or the 1 over the 1 minus beta to the power k appearing. Okay. I can stick that into here. And then what I get is that 1/2 the sum over k times pk, the right-hand side, should be the same as gamma times 1/2 sum over k times qk times 1 minus beta squared. And that is going to be, yeah, the gamma will cancel the 1 over gamma. So that is out. And then I'm going to get the 1/2 sum over k times pk divided by 1 minus beta k. And let me just put the 1 minus beta squared up the front. Okay. Okay, that's exactly my equation. That's where it comes from. Okay, that's very nice. Now I know how to choose beta. One little catch. I now have this beta. The beta is very nice. It's a beautiful solution. But what was I assuming? I was assuming that this was the extinction probability of a certain vacuum. And that's no longer obvious from this equation, at least not to me. It turns out that it is. It just happens to be exactly that. And that's a 3-line computation. And maybe I should do that. Last remaining minutes. I'm sorry? Okay, so what does this beta satisfy? Well, beta should be the sum over k, it's the extinction probability of the...
Go below the shadow, below the shadow. Yeah.
Go below the shadow. Beta should be the sum over k, qk star, beta to the power k. And where qk star is the size bias distribution minus 1, and this is related to, are you starting from a vertex or are you starting from a half edge? Here we're starting from a half edge. And this is just k plus 1, qk plus 1, divided by sum over I times qi. That's a nice probability distribution. Okay, and now I stick in what my definition for qk was. qk had some normalization constant, but that's going to drop out because I have a ratio here. So that's nice. So I can just stick in what the dependence is. Here I'm going to get k plus 1, pk plus 1, divided by, sorry, beta to the power k, divided by 1 minus beta to the power k plus 1. And then I need to renormalize that by, well, the sum over I times pi divided by 1 minus beta to the power I. Okay, a little bit of algebra. Right, but I know something about this. Right, because that's basically what comes in my fixed point equation. Okay, so that is 1 over 1 minus beta squared times this beast. So it has a 1 over 1 minus beta squared, so I might as well put the 1 minus beta squared here. And then I divide through by sum over I pi. And then here I have the sum from k is 1 to infinity, k plus 1, pk plus 1. I'm going to write this in a slightly unusual way. That's an identity. The ones are going to drop out. Oh, the other way around. Yeah, there's a minus sign involved here somewhere. Okay. I have a 1 minus beta squared here. I get a 1 over beta from there. These computations always take more time. I get 1 over beta, and I had a 1 minus beta squared here. I put a minus sign in front because a minus sign here. Okay, so there's two terms. There's this term, which is just a complicated way of writing 1. And that 1 is going to have a 1 over beta, and it's going to have this term, and then it's multiplying the first moment of the p case, which is going to cancel that. So that's just going to be a 1. And then the minus 1 here, take out the term on the right. Did I do this correctly? I made an error somewhere. Where did I make the error? I should not have made that split. Because, okay, never mind. In the end, what you get out, I've made an error here somewhere. This 1 minus beta squared comes from my fixed point equation. And then the beta squares drop out, and you get a beta in the end. So it is the survival probability. All right, let's take 2 more minutes to say where all of these other weird terms come from. These objects, we know what they are. They're nasty products of this kind. If I look at what this ratio is, actually, it turns out that these degrees all cancel out because they appear in the same way on both sides. So I actually only get these double factorials, which are factorial. And factorials you can use Stirling. If you do that, then you get exactly this term. All right. The last minute. Of course, we can't do this. So we have to undershoot n a little bit, and then somehow with switches make sure that you get exactly the right n. That explains why we actually get an error, which is e to the power smaller of n, because we need to make smaller than n number of switches in the end, and each one costs a constant penalty. That explains the errors. Where does the main factor come from? Well, I explained that. That's from here. Basically all of these terms. So that's nice. A final thing is, how is this related to my open problem? Okay. In my open problem, I was trying to shoot for local central limit theorems in the configuration model for the degrees in the giant. Well, if I were to know that I can exactly hit n, then I'm in much better shape, right? Because then actually I know that I have exactly the right thing. But then I also need the probability that the configuration model, actually the giant in the bigger configuration model, will actually exactly hit a certain limiting degree proportion. That's a local limit theorem. So if we were to be able to do that, let's say in the finite regime degree case, then we would be able to not only get the first order asymptotics or the exponential order asymptotics, but even the fine order, all the way up to the constant. And you will see weird powers of n appearing, because every central limit theorem is, every local central limit theorem is going to give you a factor 1 over the square root. That's quite peculiar. So that's the relation to the open problem. And I would really be happy if that could be resolved. Now that would be for finite degrees. For infinite degrees, we actually have no idea how to do that, because then you would need infinitely many local central limit theorems. That seems a bit tricky. So I really don't know what's happening. All right, that was all that I wanted to say. Well, I wanted to say more, but I didn't have time for it. So we'll end here. And of course, I do realize that I'm the last speaker, so let's postpone the questions for 2 minutes. I would like to really thank the organizers. Frank, Rajat, Siva, where are you? Yes, there. This has been a splendid meeting, which you've very well organized. Wonderful lectures, wonderful people, great atmosphere, nice open problems, people interacting with each other a lot, and we had a tremendous amount of fun. That would not have been possible without your dedicated efforts for this. But I particularly would like to thank Siva, because Siva, in all of this turbulent times, has been a beacon of light for all of us, solving problems around visa, canceled flights, people with stomach issues, lost bank card, you know, everything. You have a problem, run to Siva. He will solve it. So, thank you very much, Siva. All right.
Okay, before I think we have some, but we will have some questions for the talk.
Yeah, okay. So your entire point about when the degrees are infinity, we don't know what to do. So what I'm wondering is, what happens if, let's say, the maximum of the degree is allowed to grow with the vertex size, but like really, really slowly?
Yeah.
And we still keep all those assumptions, right? Those expectation conversions, second moment conversions, all of those.
Let me be very precise. For the result that I stated, we do not need the finite number of degrees, except in main theorem 2. I didn't say anything about this. But this relies on a large deviation result that Rajat already mentioned of Bordenave and Caputo, and they assume that the degree distribution is finite. If we were to have an extension of that result to infinite degrees, we would also be able to lift that condition from here.
Right.
So we don't need that. But for the local limit theorems, yeah, I don't really know how to think about local limit theorems with infinitely many random variables. That is fairly unusual territory.
So I mean, at least like in the local, it would actually be more like finitely many things, but like as you're like getting the vertex set higher and higher. Yeah. So like the stuff that's, you know, like that mass that's going to infinity, quote unquote, is actually going to be very small because we're going to assume those expectation convergence assumptions over there.
Yeah.
So I mean, basically what I'm wondering is where exactly does your proof break down if we try something, if we try that relaxation?
Well, we don't prove anything for this better errors.
Right.
You would need it for the better error, so our proof just works as it is.
Right.
For example, if you were to know, let's say, a sharper central limit theorem for the giant, I'm guessing that you will be able to change this to something of the order capital O square root of n, or maybe square root of n times log n, because then you could coach your wanted little ni's a little bit better, but you should still need to undershoot, and the amount of penalty, the error there literally comes from the amount you undershoot, because for every undershoot you need to make a switch, and that will cost you a constant penalty. So then you would be able to improve this a little bit.
Right. Actually, the reason I'd asked about this is because I think the extension to the relaxation I was talking about is probably going to be quite important for the project that my group is currently working on.
Okay. Then you need to tell me more at some point, but maybe not now.
Maybe one.
Yeah, very, very quick. This condition E, where did it come up?
Excellent. Yes, this comes up all over the place. You haven't seen it. But it does come up all over the place, and it's a good question. Well, I mean, in the most direct way, how it came up in our proof is that we need some continuity of this beast in terms of p, because we're going to be truncating the degree distribution a little bit, you know, removing the large values, etc., etc. And then we need that this object is continuous, and for that you need this. Things can go wrong close to 2. That's also very natural, because when this expectation is 2, then a connected component will look like 3. And that's very unstable. I would believe that there are really problems there, and that it becomes much harder if you were to, let's say, go to this value and ascend to infinity approach it. This, yes, very good point. I did not get round to proving this. Well, I was using that the beta is not 0, and that assumes that Q1 is positive, and Q1 positive is the same as P1 positive, so there it comes up. But it's much more easy than this, because if there are no vertices of degree 1, then you can actually compute the probability that the configuration model is not only simple, but also connected. I've done that with Lorenzo Federico. And then that probability will also converge to some Poissonian probability of there not be any cycles and not any sort of stretching or something like that. So there we can actually go much further, because then you would have the number of connected grounds up to a constant. smaller one hair. So that's not the interesting regime. The interesting regime is this large deviation case, where that's what this shows. The probability that the configuration model is connected is actually exponentially small. That's exactly what this shows.
Yeah, I think we'll have many more questions, but we have to have some closing words also. We call the bosses.
Okay, yes, we've come to a beautiful workshop, and there was also a beautiful school before. And I think I want to start by saying, well, Remco pointed to, thank you, Remco, for pointing to all the wonderful things that happened to this workshop. And as organizers, of course, you always hope that these things are going to happen. And they did happen in many respects. We want to thank the ICTS for hosting this meeting, the Networks program for supporting this meeting in many different ways. And yes, how can I describe the role of Siva? I said you're infinite dimensional. You can say you could say he's the Lebesgue measure, or he's uncountable. And all of these things are working, and we've had lots of fun to make that all work.
I just make noise. Everybody who works is standing in the last row from ICTS. You can thank them, especially for everything.
Wow. Yes, things can only run smoothly if there's a lot of wonderful things happening in the back. Now, we're already thinking about the future, so there's already a vague plan coming up that sometime in 2028 we'll have another meeting here. So if that happens, then you will hear about that. Everybody have a safe
Yeah, I just
trip
want to
home.
also thank all the 6 leads for the 6 projects, because it was an immense amount of work working with the students. I hope there will be a conclusion of this also, a nice conclusion, and you will keep working. So we'll be nudging you sometimes to know how is the work going on. So yeah, a special thanks to all the 6 leads of the projects. Yes. Thank you. Thank you. Thank you.